Ready to take a test on Friday?
No.
Oh, not yet, but by Friday you will be ready, right? So let's jump right into it. Today is review day. I posted this review sheet for you out there over the weekend. I think actually last Friday's when I got it up for you. So you've had plenty of time to figure out which ones you don't know how to do and which ones you do know how to do. So let's do the ones you don't know how to do. Questions? Where do you want to start?
Number 2.
Number 2. That's kind of a bad sign when you start.
That one's hard.
Actually, yeah, that one is. Usually I have a lot more definition kind of stuff in the beginning. I just went right to the problems on this one. So number 2 says, let A be the event that a person lives in Atlanta. Let B be the event a person works at the book factory. Notice what I did there? A, Atlanta, B, book factory. For the 2 events, A and B, probability of A is 0.6, probability of B is 0.4, probability of B given A is 0.5. Now find the probability of A given B. There's two points to this problem. One is how do you work a problem like this, but more importantly even is that those are not the same thing. That's a common misconception that it doesn't matter which direction you do that conditioning, but it does matter. So you won't get the same answer. Sometimes you do just by coincidence. But so what we want, what it says to find is the probability of A given B, right? A given B. So what's, by definition, what is A given B? You got a question?
No, I was just going to say it's the probability of A and B over the probability of B.
Good. It's the probability of A and B over the probability of B. At that point, you stop and check, did they give me those pieces that I can just plug in and I'm done? They gave me probability of B, but they didn't give me probability of A and B. Right? They gave us A, they gave us B, they gave us B given A. So now I have to use another rule. So what's the probability of A and B? Multiplication rule. So that's the probability of, what's the multiplication rule?
A times.
Probability of A times probability of, is it B, stop, or is it B given A? Right? It's probability of A times probability of B given A. Or it doesn't matter, A and B are interchangeable, so you could do B and then A given B, but that doesn't help you because that's what you're looking for. Right? Now why can you not just do probability of B? That only works if what? If they're independent. Are they independent? Well, we don't know, right? They don't tell us they're independent. We'd have to check and see. But this always works, so use this one. Now that's over probability of B from already being there. So now I have all of those pieces. So the probability of A is 0.6. Probability of B given A is 0.5. And the probability of B unconditionally is 0.4. So when you multiply all that out, what do you get? 0.75. Oh yeah, it would be because 0.6 times 0.5 is 0.3. So I got 0.3 over 0.4, 3/4. All right, next question. And whenever I finish a problem and I say next question, if you're still struggling a little bit, now why'd you do this? Make sure you stop me and you ask that. You had your hand up? Somebody else?
Yeah, number 6.
Number 6, okay. Number 6 says the following contingency table provides a crosstab of smokers and exercisers. So we have data like this from our class. This is same stuff, but an older data. But we've got a series of questions asked about probability. So I'm scroll that down a little bit so I can write right on there. Part A says, what is the probability that a randomly selected person from this table is a non-smoker? All right. So you have to figure out how to read this darn table. But smoke is above this column, so these are non-smokers, smokers. And then this is non-exercisers, exercisers. So I'm going to add that here. This is exercise, and this is smoke. Right? So, probability that they are a non-smoker. So, which two numbers do I divide?
415 divided by 35.
So, non-smokers, there's 415 of them. Notice that sentence says nothing about exercising. So, it's a marginal total that you need. So, that one's 415 out of 505. Okay, and then part B says probability that a randomly selected person is either a non-smoker or an exerciser. Uh-oh, the word or. What does the word or tell you to do? Addition rule. So, addition rule, I'm going to use S for smoke and E for exercise. So, the probability of smoke or exercise, by the addition rule, that's the probability of smoke plus the probability of exercise minus, you're not done yet, probability of smoke and exercise. Good. Good at these today. Okay? So now we just fill in the pieces. The probability of smoke we just did up here. So that's 415 out of 505. And the probability of exercise. And that's marginal because it doesn't say anything about smoking. So exercise are the yeses for exercise, and there's 247 of those. So that's 247 out of 505. And then minus the probability of both. So probability of a, oh, I just realized, I'm using an S. I should be using an N for non-smoker, right? Because I just saw smoker. It's non-smoker exercise. So let me fix that. So I'll do NS for non-smoker. Okay, still the 415 because that one says non-smoker also. Sorry about that. I'm getting in a hurry and I do stuff like that. So now non-smoker and exercise. There's 222 people that meet both conditions. And the reason we subtract it off, because those 222 people are part of that 415 and they're part of that 247. So they got double counted, so you subtract them back off once. So minus 222 out of 505. So what is that as a fraction? Somebody do that math for me. 415 plus 247 minus 222. 440? So as a fraction, that's 440 out of 505. And then what is that as a decimal?
0.8713.
87. What? 13. That? Okay. So 87% of the people in this table are either non-smokers or exercisers. One way to think of it. So part C, what is the probability a randomly selected person from this table is a non-smoker given they exercise? So probability of a non-smoker given they exercise. Well, you could use this rule for conditional probability, and that'll work just fine. But when it's in a contingency table, it makes it easier if you just work with counts instead of probabilities. So instead of probability of A and B, you just say how many met both. How many were both non-smokers and exercisers divided by how many, right? Because the denominators end up canceling anyway. So how many, what does the condition on E tell us to do? We look at only this yes column for exercise. So now my whole problem is reduced to just those 247 people. So that tells you the denominator is now 247, not 505, because they have to meet the condition. So this is going to be 247 on the denominator, and on top, 222. Okay? So what is that as a decimal? It's going to be pretty close to 1, because that's almost all of them. 0.89. 0.89. Give me two more decimal points. 8989. Thought I was just hearing you wrong. Okay. Part D. Would you say that being a non-smoker and being an exerciser are independent events? Show why using probability. How do you check to see if two things are independent? By looking at probabilities. Well, one way is to do what we were doing over here. We said if A and B were independent, then you could do the AND this way. But if they're not independent, it won't work. You have to use the condition. So you could check and see, well, does it work? Could I do probability of non-smoke and exercise using the multiplication rule for independent events, which is the one where you don't condition on that second part? If they're independent, this should work. Let's see if it does. In S and E, we already did right here, right? So that's 222 over 505. And I'm going to put a question mark above the equal sign, because that's what we're checking. Are these equal? Then NS times E. Well, NS, we did up here, that's 415 over 505. And E would be 247 over 505. We did that one right here, 247. Now, unless you're better at mental math than I am, you can't look at those and go, oh, those are equal, or oh, they're not. I got to convert to decimals. And then I can see each side of the equal sign if they're the same. So do the left-hand side, what do you get? .4396. Okay. Okay, now do the other side. It's going to take you a little longer, so hopefully you've already started. 415 times 247 divided by the product of 505 times itself. I got .4019. Are they equal? No. They're not too far off, but they're far enough off that you couldn't say, yeah, they're the same. Right? Remember, with real data, they're never going to be exactly the same. So you're kind of doing the eyeball test, but that's fairly different. So I'd say, yeah, they are not independent. Since these are not equal, they are dependent events. Yes? Nice voice today, huh? Let me get closer. If it's .43, yeah, if it was .4319, that'd be close enough to that one to say, I'd call them independent. Right? And this idea of, well, how far off is far enough, it's kind of hard to tell. When we get to I think it's the very last lesson that we learn this semester, we'll get a statistical hypothesis test for independence in a contingency table. Right now, all we have is the eyeball test. So we just look at the numbers and go, they're pretty different. Right? There are other ways to check for independence. A really strong way, we won't work it out, but another really good way is is the probability of not smoking conditioning on they do exercise, is that the same as the probability of not smoking given they don't exercise? Right? Because if they're independent, it shouldn't matter whether or not they exercise. So conditioning on them exercising, conditioning on them not exercising shouldn't change the probability if they were independent. So do these two. This will show differences bigger than this one will. So if you get to this one and you go, I'm not sure if that's far enough apart, so that's kind of in the gray area, do it this way and that'll answer the question. They'll either get closer together or they'll get further apart. All right, everybody good on that problem? Yep.
Number
14, okay. Okay, good. I was hoping somebody would ask this question because these are the ones that people kind of struggled with a little bit, all the normal probability problems. So number 14 says, the process of manufacturing a ball bearing results in weights that have approximately normal distribution. Ooh, big hint right there. If it says this somewhere in there, you're probably going to be doing normal CDF or inverse norm, right? With a mean of 0.15 and a standard deviation of 0.003. Okay? So, suppose you select one ball bearing at random. What is the probability that it weighs 0.148? So probability, I like to write this out, what it's asking me in symbols. It helps me figure out what I'm going to be entering into my calculator. Probability that a randomly selected ball bearing is equal to 0.148. Which function do you use on your calculator for that? Trick question. You don't use your calculator for that one. You should know the answer. 0. Why is it 0? Because x is a continuous random variable. What's the probability that a continuous random variable takes on any specific value? 0. Remember that's an oddity of continuing. Caitlin's back there frowning like, what? Now remember I did that thing with the uniform variable. I had you might not have been here, but we generated continuous uniform variables with our calculators, and I said I'd give you $1 million if you hit 0.5 exactly, because you can't hit any value exactly, right? If I measure the weight of this ball bearing to 1,000,000 decimal places, I guarantee it is not exactly 0.148. Right?
So how do you know it's continuous from the
Well, good question. How do you know it's continuous? Because it never says that. But normal distribution is a continuous distribution. That's one way to know. The other is just thinking about weights. Well, anytime I measure something like that, it's going to be continuous if theoretically I could measure more and more and more decimal places and get more and more possible answers, then it's continuous. But if I ask you a question like, how many brothers and sisters do you have? Then that's not continuous because you can't measure more accurately than to the nearest whole number. Okay, part B. Select one ball bearing at random. What's the probability it weighs less than 0.148? Now, is that possible? Yeah, that's, when it's continuous, you can't get an equal sign. You're always going to get 0 in that case. But it's intervals, right, or regions that we can compute probabilities for. So what's the first step here? Draw a picture. So it's normal distribution. They told us that. It's centered at 0.15 because that's what they said the mean was. The standard deviation is 0.003, So halfway down the hill should be 1 standard deviation in each direction. I need to know what those are so that I know where 0.148 goes. So subtract 1 standard deviation from 0.15, and what do you get? 0.147. So this dotted line is at 0.147. Now I know where my 0.148 goes. It goes 2/3 of the way down to there, right? So it's about right there. So that point is 0.148. Now I shade the region that I want the area of, and I give myself a ballpark estimate of what you think it's going to be. Right? Well, I heard somebody, what did you say? 16%. Bigger or smaller than 16%? A little bit bigger, right? And she got that 16% because that's what it would be if it was here at the dotted line. By the empirical rule, 68% is in here, leaving 32%. Half of 32% is 16%. So from there it would be 0.16. So this is another third of the way up. So it's going to be bigger than 0.16, but probably not a lot bigger. So let's say 0.2. Right? So my BP, ballpark estimate, is 0.2. Now we can go to the calculator. Now remember, the book tells you, okay, compute z-scores, do all this stuff. And they even have you use your calculator once you get the z-score, but there's no reason to do that. You can go directly to the answer. So this is equal to normal CDF, but tell me what to enter. You have to enter 4 things. Okay, negative infinity, 0.148, 0.15 is the mean, 0.003 is the standard deviation. Okay? And then what does that give me as an answer? 25249. Okay? Is that close enough to our ballpark estimate to think, yeah, that's probably about right? Sure. If you had accidentally reversed this and went 148 to 999, that'd be a common mistake. Your answer would have been 1 minus this. You'd have got 0.75. You'd look at your ballpark and go, wait, that's too big. Right? I must have done something wrong. You go back, look at your calculator, and say, oh yeah, I flipped those. Okay. Part C, what is the 95th percentile of ball bearing weights? That's your inverse norm. Percentiles are inverses. So this is going to be inverse norm of 0.95, because the inverse norm function is a percentile function. So if you're just asked to find a percentile, you just put that right in there. The next one will also use inverse norm, but it's not so simple. Right? But then this will be 0.15 for the mean, 0.003 for the standard deviation. Right? Now ballpark estimate, 95th percentile. If I add 1 standard deviation, I get 153, and that would be the 84th percentile by the empirical rule. So 90th percentile, or 95th percentile, would be a fair amount on past that. So I'm looking at, I don't know, 0.16 maybe. And that's not a probability, they just happen to be decimals. Okay, so what do you get when you do that? 0.1549. And I guessed 0.16. This is a little small. I was guessing a little too big, but close enough. Okay, now the next one is more difficult. Find 2 numbers such that the middle 90% would have weights between them. So if I come over to my, I'm going to draw a new picture. 0.15, halfway down the hill is 0.147 and 0.153. In between there is what percent? 68%. I want 90%. So I got to go further out. But I don't go all the way to 2 because that would give me how much? That'd give me 95%. So I want a little bit inside of those. That's my ballpark estimate. Right? So 0.90 in the middle. So call this one L for left and this one R for right. We need to solve for L and R. So L is inverse norm. I heard 0.05, I heard 0.1. One of those is right. It's 0.05, right? Because it's the area that's to the left of whatever number you want, right? And there is not 10% of this that's left of L, because there's 90% in between here, 10% there would be all of it, and I've still got area left up here, right? So I have to take half the leftover area. 90% is the area, left over is 0.1, and half of that would be here, half of that up here. So 0.05, 0.15, 0.003. And that is 0.145, call it 1 if we go to 4 places. Right? And then, what about R? Yeah, we've already done that one, haven't we? Inverse norm of 0.95, same, the rest is the same. 0.95 because from R down to negative infinity, how much area is there? Well, there's 0.9 to get down here to L, and then there's another 0.05 down there, so I add those two together, and I get 0.95. But we already did 0.95, so I was saving you time. 0.1549. Okay? So there's your how's it worded? Find two numbers. There's your two numbers. Okay? A good check that you got these right is that when you subtract the bigger one minus the smaller one, you should get what? The middle area they ask you about. Right? So if you mistakenly put 0.9 here in one of them, you subtract, you're not going to get what you expect to get. Okay, part E. Suppose you select a sample of 100 ball bearings at random. What does the central limit theorem tell us about the sampling distribution of the sample mean x bar of those 100? And then what is the probability that the sample mean is less than 0.148? So the same probability they ask for here, but now it's the mean of 100 ball bearings, not a single ball bearing. Right? So we would write that expression as probability of x bar less than 0.148. Now on the test Friday, I might not be nice enough to ask you this first question. This first question was designed to let you know, oh, here comes a central limit theorem question. Right? But you may have to figure that out on your own. So what does the central limit theorem tell us about the sampling distribution of x bar?
It's the same as the population.
Okay, the what is the same? The mean is the same. So the mean of x bar is the mean of the x's. Right? So sampling distribution center is the same as the population distribution center, and those are both 0.15. But then sigma x bar, which I call standard error of x bar, is equal to what?
Standard deviation of the population divided by the square root of the sampling distribution. Sample.
Good. So it's the standard deviation of the population distribution divided by the square root of the sample size, which is 0.003 over the square root of 100. Now I use numbers I could do in my head. Square root of 100 is 10. divide this by 10 and you get, what does it do when you divide a decimal by 10? It moves the decimal one more place, right? So this is 0.0003, one more zero in there. So now I'm ready to do this probability. I guess there's one more thing to answer about this first question before we go to the second question. It says, what does it tell us about the sampling distribution? There's three characteristics of the sampling distribution, and we've got two of them. We've got the mean, we've got the variability. What's the third one? What'd you say, Tyler?
Sample size?
No, that's not the characteristic of the sampling distribution I'm looking for.
It's normally distributed.
It's normally distributed, the shape of it. So there's three characteristics of any distribution. Its shape, its mean, its variability, right? So we've got the mean and the variability. We need to know its shape. Well, since the sample size is 100, that's bigger than 30, so we know that x bar will have a normal distribution. Now, what if the sample size had been only 5? Would we still have a normal distribution? In this problem? Yeah, we would. Remember that condition, the if part of the central limit theorem is if x is normally distributed or you have a sample of at least 30. So in this case, the x's are normally distributed, right? They have an approximately normal distribution to start with, so sample size doesn't matter. But either way, you're bigger than 30, so it's going to be normal. That tells me that this probability can be done using the normal CDF function. Now I'm going to dispense with drawing the picture, drawing it detailed, but actually I can't resist. Let me use a blue marker. Where will that distribution look like compared to the one that I already have drawn there? If I draw the sampling distribution of x bar onto this same scale, what's it going to look like? More narrow and taller, right? But it'll be centered at the same place. That's what we just decided. So it'll look like that. A lot taller, and I'm out of board, but, right? So now, ballpark estimate of being less than 0.148. Very small probability. Right? So when I do it, I expect to get a really little number. So do it. Negative infinity up to 0.148, mean of 1.5, and standard error of 0.0003. So it should look identical to this one that we did for individual ball bearing, but the standard error instead of the standard deviation. This is the only thing that changes. It's the only thing that changes because they ask us for the same region. Okay, so what do you get for an answer there?
It's 1.315 times 10 to the negative
1.315 times 10 to the negative 11. So in your calculator, you'll see an E minus 11 out there on the right-hand side. Don't forget about that. Don't put 1.35 down as your answer and go on. Remember, probabilities have to be less than 1. Yes?
This one you said we have y as your sample size will still be normal distribution.
Because the central limit theorem, did everybody hear her question? Probably not. She said, you said even if the sample size had only been 5, x bar will still have a normal distribution. Why? And that's because the central limit theorem tells us that the if part says if x is normally distributed, right, the original population distribution, if it's normally distributed, or even if it's not, you have to have a sample size of 30. But we are normally distributed to start with, so sample size doesn't matter. Okay? Next question. 15? Okay. Okay, 15 says, an exit poll in a recent election was conducted to predict the winner during the evening news prior to the polls closing. If, let's see, if 1,000 people were randomly selected as they left the polls, this is called exit polls, and 53% say they voted for Cletus Aardvark, if the truth in the population is that it was a tie, right? Now, why did they say that? If the truth is it's a tie, what would a tie mean? Yeah, 50% voting for that candidate, and it's you can't predict the winner, right? So what they're getting at is, can you predict the winner? Can you predict that Cletus Aardvark's going to win if he's got 53% of the vote for this sample? So if the truth is that it's a tie, what is the probability that a poll of 1,000 could have a proportion of 0.53 or higher? Would you be willing to declare him the winner based on that? So what does it ask for? I like to start with a probability statement. It says, what is the probability that a poll of 1,000 people could have a proportion of 0.53 or higher? So what's the symbol for a sample proportion? Not X bar. It's proportion, P for proportion, right?
P with a hat.
P with a hat. Right? So P hat is greater than or equal to 0.53. That's what it says. Sample proportion of 0.53 or higher. So now in order to compute that probability, I need to know, well, what's the distribution, the sampling distribution of P hat? That's the sample size, but what's the sampling distribution?
Is that if the truth of the population is a tie?
Yeah, if the truth is that it's 0.5, which is 50%,
It's not a bigger population.
that's not the probability. Oh, well, depends on what you mean by that. Expand. Probability of what?
Of the population.
Okay? That's P, right?
Yeah.
That's the population proportion P. I thought you were saying it was the answer to this.
Oh.
Okay. And that's why I said no, but then I realized, oh, she's probably talking about something different. What do you use? What's the distribution? I know the population proportion P, so remember my little given thing? You write down what's been given. They gave us that P is 0.5. They kind of disguised it in there, but that's what that 50% means. What else did they give us? Okay, they gave us N. N is 1,000. And they gave us the P hat that they're interested in, right? So they gave us P hat. And then they asked us to find this probability that I already wrote down. But from there, from those things being given, I have to know how to compute this probability. Okay.
So the square root of P minus P over.
You'll need that, yes. But that's not the probability. But what is that?
That's
Standard deviation.
standard error.
Yeah, that's the standard error of P. So we're going to need to know the standard error of P, right?
And then
What's the distribution going to be? Hint, central limit theorem. We have two versions of central limit theorem. One is for means, which the last problem we worked had that. This was for proportions. What?
must be more like what kind of
Well, the central limit theorem tells us that P hat will have a normal distribution, approximately normal distribution, if what? So by,
You have 5 successes or 5.
there you go. By the CLT, P hat will be approximately normal if NP greater than or equal to 5 and N times 1 minus P greater than or equal to 5. Is that condition met? If the true population proportion P is 0.5 and I take a sample of 1,000, I expect to get how many successes? 500. That's way bigger than 5. And I expect to get 500 failures. Remember, this is successes, failures. You need to expect to get 5 successes and 5 failures. And we easily get that. So that's met. So p hat will use a normal distribution. Oh, that tells me I can use what function? Normal CDF. So this probability is normal CDF. But first I need a ballpark estimate. So I need a picture. P hat sampling distribution will be centered where? At P, the population proportion, which in this case is 0.5. Now remember, that's really unknown. And in real practice, that's the way it is. You don't know what it is, so you make a guess and you say, well, if that's what it is, right? So if it's 0.5, then my standard error is how much spread there is in this distribution. So I need that standard error. And that's what Caitlin was trying to give us a minute ago. So the standard error of p hat is equal to, well, give me the formula first.
Square root of p times 1 minus p over n.
Right? 1,000 for n. Now notice, I put in p, not p hat. Later, after the test, we will start a section where we won't know what p is, so we replace it with p hat. And that's okay. Here, they're close. You'd get a number that's almost the same, but you'd be off a little bit. But okay, so what is that number?
0.0158.
0.0158. Okay? Now you were starting to give me a different number a minute ago. Did you see what the difference is?
Yeah, I was just gonna tell you what to write.
Oh, I see. Gotcha. You were, okay. I thought you were giving me the answer on it. Okay, so that's my standard error. So if I add that and subtract that from 0.5, I'll know what goes under these dotted lines. So the adding in I can do pretty easy. 0.5158. The subtraction is not so easy, but it'll be 0.48 something. Anybody have it?
4842.
42. Okay. So now where does my 0.53 go? Well, it's bigger than this number. So it's over here to the right. In fact, if I go 2 standard errors, what am I up to? 0.5316. So my 5.3 is just a little bit inside of that. So give me a ballpark estimate. What'd you say?
0.025.
Okay. But a little bigger than that, right? Because
Yeah.
from 2 standard errors up would be 0.025, right? 2.5%, half of what's left over from 95%. So this is a little bit bigger area than that. So, what do you think?
0.026.
Did you already work it?
Yeah. But it makes sense. I mean,
Yeah, it does.
said.
She said ballpark of 0.026, a little bit bigger than 0.25. So yeah, that works. I probably would have said 0.3, but I would be overestimating a little bit. But doesn't have to be perfect. So now we can fill in normal CDF. What are my bounds? Lower and upper.
0.53.
Okay, 0.53 to infinity. 0.5. And then 0.0158. Then I'd probably recommend at least one more decimal place of accuracy there because I want to keep 4 on my answer. Does anybody know what the next one is? I didn't write it down over there.
1, 1.
So it's 15811,
Yeah.
1, like that. What they recommend in the textbook is to just type that whole thing out in there, and then you don't have any round off error. But it gets to be an awful lot to keep track of in one expression, and screen scrolls down and everything. So this should be fine. So what is the answer? 0.028. Give me one more place. 9. 0.289. Okay. Our ballpark estimate looks about right. Call it good. Now, would you be willing to predict the winner? Would you say that you have strong enough evidence to go on national news and go, I declare Cletus Aardvark is going to win this election? What's the probability you're wrong? If you say he's going to win, what's the probability you're wrong? 0.289. What's the probability you're right? About 97%, right? So you got a 97% chance you're going to be right if you declare him the winner. So what we use as the cutoff for being willing to declare is about a 5%. If I only have a 5% chance of being wrong, then I'll suck it up and say, okay, I'll stick my neck out and I'll say, I believe this to be true. So my answer would be, yeah, I'd be willing to declare him the winner because that probability is pretty small. You're not going to get, it's very unlikely you would get 0.53 in a sample if he is not going to win. And this is the extreme of not going to win, right? You're not going to win at 0.5 or anything less, right? So if it's exactly a tie, then it's very unlikely you could get 0.53 in your sample. But you did get 0.53, so that assumption of 0.5 is probably wrong. I'll say, no, I think he's got more than 0.5. I think he's going to win. All right, next question. Yep. 20. Okay. Ah, good. This is a good one to follow up with. At a university, 60% of the 7,400 students are female. It's a good place for a guy to go to school. The student newspaper takes a random sample of 50 students and surveys them. They report that 25 of the 50 in the sample were female. Find the mean and standard error of the sampling distribution of the sample proportion of females. The mean and standard error. Well, the mean is easy. What's the mean of p hat? It'd be 0.6. The mean of p hat is the mean of the proportion in the population. They tell us that 60% of the students are female. So p is 0.6. So the mean of p hat will be p, which is 0.6. Right? So equals p, which is 0.6. Then the standard error. The standard error, the formula that's still on the board over there, which is the square root of 0.6 times 1 minus 0.6 divided by, how many did they have in their sample? 50. Okay? So give me that as a decimal.
0.0693.
0693. Okay, there's the mean and standard error. So that's part A. Now, is it unusual to get a population, or I'm sorry, not population, a proportion of 0.5 females in the sample, right? So that's what p hat was. P hat is x over n, which was 25 over 50. X is the number of successes. P hat is the proportion of successes. So it's 25 out of 50, which is 0.5. Would that be unusual? Well, there's two ways to answer that question. Think about z-scores. How many standard errors do you have to go out before you say, ooh, that's getting out there? That's pretty unusual. More than what? 3. If you get to 3, it's like, whoa, that's really rare. So we can see how many standard errors that is away from the mean to decide if it's unusual. If it's less than 2 away, you'd say, well, that's not unusual at all. If it's between 2 and 3, then that's kind of unusual. If it's more than 3, hey, that's really rare. Right? So let's do that first, and then we'll come back and talk about probability. Z is the sample proportion 0.5 minus the population proportion 0.6 divided by standard error. Right? It's the standard deviation of the sampling distribution, which we call standard error. 0.693. Give me that as a decimal.
Negative 1.44.
Negative 1.44. The negative just tells us that it's less than what the population proportion was, so that's not a big deal. But it's 1.44 standard errors below. Is that unusual?
No.
No. So the answer is no, that's not unusual to get 50% in your sample of size 50 when the population has 60%. But if I wanted to answer this question with probabilities, we could use our normal CDF function and do probability that p hat is less than or equal to 0.5. Why do I have to put the or equal? Why can't I just put equal 0.5? Because it's the normal distribution I'm using, and that would be 0, right? So you need a range. Well, since we're thinking that 50% in the sample is unusual, or we're wondering if it's unusual, then anything less than 50% would even be more unusual. So this is as unusual or more than what we got in our sample. And if we compute that probability, then we would find that it's, like 25% chance of that happening or something. Not an unusual probability. Definitely not less than our 0.05 that we talked about a while ago. Okay, so that concludes today's episode. You can go, actually I don't remember if I posted the key yet or not. If it's not out there, email me. The key's ready. I got it up for my online class, but I don't think I got it on yours yet. Okay. So you can get the key and look at the other ones you didn't get to, and then email me any questions that you have. Or stop by and see me. So we'll see you Friday.